Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 13 in our incredible new tutorial series where you're knowing where you're going with your ultimate GPS tracker project. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, let's go ahead and take a couple of minutes and review where we are in this crazy class. We are now on lesson number 13. We have completed 12 lessons. And where have we ended up with so far? We have a GPS tracker project based on the Raspberry Pi Pico W and the Ultimate Adafruit GPS Breakout version 3. We have an SSD OLED, SSD 1306 OLED that is showing us our lat long. We got a couple of useful buttons here, and then we've got the Sunfounder Breadvolt that will allow us to power this thing remotely. Now, all of this gear, I have links down below if you need to catch up with where we are, but we've got the circuit built, we've got the code running, and you can see that we are reporting live latitude and longitude. We've got the date and the time from the atomic clock. We're showing the number of satellites. I'm sporting 9 satellites right now, and if we press the button, we'll switch over and we'll get our speed, which on the desktop is very close to 0, the heading, and our altitude in meters. And so this is all very well and good. But now we need to do a little math today, because what I'm going to show you, this will give you latitude and longitude of wherever you are. But something that's very useful in our project would be if we could calculate the distance between two of our positions. Like if we start here and end here, how far did we go? You could actually use this as a way to measure things. You could start at one end of your yard, and then you could go to the press the button, go to the other end of the yard, press the button again, and then based on those two GPS coordinates, it could tell you the distance between those 2 points. Sound good? I hope it does. So let's hop over here and let's jump in and let's see if we can start talking about how that would work. So to do that, we got to go back and think a little bit about circles. And so I'm going to see if I can draw a circle here. Hey, that was pretty good, wasn't it? I would say that is a pretty good circle. And now what we want to talk about is what is the circumference? That is, if you started here and you went all the way around, and let me kind of put a center here. We'll kind of draw a vector. And if we started at this point and then we went all the way around through 360 degrees, which is in radians, 2 pi radians, we would go how far? Well, we know that the circumference is equal to 2 pi times the radius. The circumference is 2 pi times the radius. And so we'll label this radius. So that is all well and good. But what you really want to see is you can do this for different amounts, okay? So what if I came, instead of 2 pi, what if I just came theta radians? Well, how far did I go from here to here on the curve, right? I'm not flattening that. I'm going on the curve. How far would that be? Well, that distance, we'll call it the distance that we went there instead of circumference, because we're not going all the way around. That distance is equal to the theta in radians, the angle that I went through in radians, times the radius, okay? And what you know it as is if you go all the way around, theta is 2 pi. So the circumference all the way around is 2 pi r. Okay, so what we see here is this equation is just a little bit more of a generic equation for when you don't go all the way around. How far did you go? Okay, that turns out to be very useful. And what we're going to do is we're going to come back over here and we're going to start thinking about our GPS coordinates. And so let's see if I can make as beautiful of a circle this time as I did last time. I would say that was a fail on the first attempt, but let's not give up and let's try again like that. Okay, very good. Now, what I want you to think is, let's think that we've got the center of the Earth here. This is the Earth, by the way, okay? And now let me see if I can kind of draw the equator like this. And so I'm kind of trying to draw the equator. That was not too bad. And let's say if I stayed on the equator, or I stayed on any circle for that matter, where I'm not changing the latitude. I should do it this way. I'm not changing the latitude. I'm only moving in longitude. So let's say that I was here at longitude 1, and then I came over here to longitude 2, and I moved from 1 to 2. Okay. Now, how far did I go? Well, I can calculate it. What would it be? Well, what is this angle? What is this angle? The angle that I went through would be what? Ln 2 minus ln 1. Now, I got to remind you, when we're doing this, we got to go, normally we report in degrees, but when we do these calculations, we got to convert degrees to radians. And so what you can do is radians is equal to degrees times 2 pi divided by 360. So you take the degrees that you're comfortable with and you can calculate radians. And you can actually reduce that, and that would be degrees times pi divided by 180. That allows you to go from degrees to radians. So this theta here is in radians, okay? So the theta is the ln 2 minus the ln 1. That is my theta. Well, how far did I go between these 2 points? Well, my distance that I went is just going to be the theta times the r. And what is the r? The r is the radius of the Earth. And so if I have a situation where I am keeping the same latitude and I am just changing longitude, I can calculate how far I have gone. Now, similarly, let's see, I think it would be easier if I just started completely over. I'm going to try to get another one of those most beautiful circles that I'm becoming famous for here. So let's see. So I'm going to make it a little bigger. There's my circle. Similarly, what if we did not change? What if we did not change our longitude, but we changed only our latitude? So let's see if I can draw a great circle, okay? And let's say I started at point 1, okay? I started at point 1, and I went to longitude value 2. In that case, what is this angle? That angle would simply be the latitude. I might have said longitude, but it's latitude going up and down. So this would be latitude 2 minus latitude 1. So how far do I go if I go from here to here along that curve, right? I'm not flattening it out. Along that curve, how far did I go? The distance is going to be equal to that angle in radians times r, and the r is the radius of the Earth. So this would be an incredibly simple problem. This would be an incredibly simple problem if we would only change our latitude and leave our longitude, if we would only change our longitude and leave our latitude fixed, or if we would change our latitude and leave our longitude fixed. We could always calculate it with this simple equation, but what is the problem? Between two generic points, I have a change in a change in longitude and a change in latitude. Now you could calculate it as this distance plus this distance, but you're not driving around like that. You're driving straight between those 2 points. So we have to figure that out. And that turns out to be a little bit tricky. So let's draw our circle again. Let's draw our circle. Okay. A beautiful circle, I must say. Okay, so now let's come here. And let me get that a little bit more in the center. That's pretty good. Okay, I'm going to draw my equator again. I think that's a pretty beautiful equator, even though I say that. And then let me also draw a circle where I'm changing the latitude. Okay, so now let's say that I start here, okay, and then I go over to some latitude, which is here, and then I go up to some longitude, which is here. So I go from here to here and from here to here. But I wouldn't drive around that way, right? I would want to go straight from this point to that point. So this is point 1 and this is point 2. How far did I go? That did not draw good, did it? Okay, let's see if I can draw that a little better like that. Okay, I'm trying to show that that is a curved point, okay? So how far did I go when I went from here to here? And this is point 1 and this is point 2. So what does point 1 have? That is going to be like a lat 1 and a lon 1. And then the point 2 is going to be a lat 2 and a lon 2, like that. Okay, so those are just what? 2 GPS points, lat, comma, lon, right? So you're with me here. So we're going from this point 1 to this point 2 along this direct path. How far did we go? Well, what I need is I need to draw from here to here and then from here to here. And what do I need? I need this included angle. Okay, I need this included angle. Does that make sense from the center of the earth to this point, and then I go over and I go up, but I need to know the angle from here to here when I'm doing it directly, right? I have a change in longitude and I have a change in latitude, but if I go directly, I need that angle between those 2 points and the center of the earth. And the problem is it's not simple like I had done before. But once I get it, once I get the included angle, once I have that distance is going to be equal to just that angle times the radius of the earth. So the whole trick becomes how to get that angle. Now, what I have is, like, you can see that I've got a bunch of triangles. And when you took geometry back in high school, remember how they called it plane geometry? And when they called it plane geometry, I always thought it meant like ordinary geometry, like we're doing plain old geometry. No, the plane meant you're doing geometry in a plane, geometry on a flat surface. That is also called like Euclidean geometry, flat geometry. Well, what we have here in this problem, is we don't have a plane. So if you think of this triangle that we just made, it doesn't have flat legs. It's a triangle, but it is on a curve and those points are curved. So what we have is what's called non-Euclidean geometry. Now, if we were just on a flat plane, you could use what you learned back in high school, the law of cosines. You could use the law of cosines. And if you have the 3 sides of a triangle, you can calculate the angles, okay? And so that is from the law of cosines. But the problem here is that we now are not in plane geometry. We're in non-Euclidean geometry. We're in spherical geometry. And so you have a whole different set of equations. And so what do I need? I still need to get this angle. I still need to get this angle. And to do that, we're going to have to use this spherical geometry. Now, there are two choices that I have at this point. I could teach you non-Euclidean geometry, or I could show you the equation. And in this case, I'm going to show you the equation because you understand what we're trying to do, you understand where we're coming from, and I think it might just be tedious if I tried to teach you the geometry. Now, I would be willing to, but you can see already that it's getting hard for me to draw, right? It's getting hard for me to draw these three-dimensional angles, so it would be very hard for me to explain the geometry to you just because it's hard to draw. So with that as an introduction, we are going to jump into the equation. And so what I will do here is I will come over here. Okay, there it is. Now, what is it that we want? What is it that we want? We want this, the included angle. And what do we have? We have 0.1, and 0.1 is the point. Lat 1, lon 1, right? Just a good old GPS point. 0.2, where 0.1 is where we start, 0.2 is where we end. 0.2 is lat 2, lon 2. So we have to have those four numbers, lat 1, lon 1, lat 2, lon 2. And then we can calculate the included angle, that sort of sideways angle that I was trying to draw. And in order to do that, if you look at this equation, if you look at the equation, all it needs is lat 2, lat 1, and lon 2 and lon 1. Now, what is arc sine? Arc sine is inverse sine, and so that is undoing the sine, and arc sine is something that can be done in MicroPython. And then I've just got a sine squared, I've got a cosine, I've got a cosine, a sine squared, and then I take the square root, and then after that I find the arc sine of all of this. And then what do? I multiply it by 2, and then I have that included angle. Now, half the battle is over, because now if I want the distance along the curve between those 2 points, it's just the r, the radius of the Earth, times the included angle. Now, when you do this, remember that you have to convert your degree, decimal degree, lats and lons to radians, and you do that by multiplying by, what did we do a while ago? We multiplied by pi and we divided by 180, and that will do the conversion for you. Okay. Now, what I also want you to see though is that, let's see if I can draw one more circle for you. The other thing that is very, very useful would be, okay, so let's say that I am going from this point on the Earth, I'm going from this point on the Earth to this point on the Earth, and what I want to know is, what heading do I need to head? Well, if this is north, like how many degrees away from north would I head? So like you think north is 0 degrees, and typically east is 90, and south is 180, and west is 270, and then north is back to 360, which goes back to 0. So if you're just wandering around on the ground, what angle would you need to walk at from north in order to get from point 1 to point 2? Now we know how far away it is, but now we need to know what direction would we walk or drive to get from point 1 to point 2. And what that is, my friend, is that is the heading, okay? I better get out of your way. And similarly, you can see that the heading is very easy, and we just use the arctan2 function. Now, arctan is undoing the tan, and if you do arctan2, which is actually a command in MicroPython, what you do is you take the arctan, and I just want you to see this comma, okay? So like arctan would be like A over B, something like that. Okay, well, what you do in MicroPython arctan2, you write that instead of a numerator divided by a denominator, you write the numerator comma the denominator. Okay, so this would be in normally how you think of tangent, it would be this divided by this, but the better way to calculate it would be to do this, comma this, and use the arctan2 in MicroPython. And what that does is that takes care of all the different cases where you can have different signs of your number. And remember, in trigonometry, you hated that because you never knew what quadrant you were in. The arctan2 function keeps track of the quadrants for you, so it makes the coding a whole lot easier. So let me let me take some of that off that is causing you confusion. Okay, so what I want you to just see is, as you're looking at it, that is a comma. So now you have an equation where you can calculate the included angle. You can calculate the distance between 2 points, and you can calculate the heading. If I'm starting at point 1, what angle do I need to walk in order to get to point 2? So that is the math, all right? That is the math. And what we want to do now is we want to add that capability to our little GPS function, because if we know where we're starting and we know where we want to go, we could calculate the distance and we could calculate the heading. Or if I press the button at point 1 and press the button at point 2, it could tell me how far apart those two distances are, and it could tell me what is the heading between the first point and the second point. Does that make sense? I hope it does. So this, my friend, is your homework assignment. What I want you to do is write a program where you input your latitude 1 and longitude 1. So that's your first point, lat, lon, input it in degrees, because that's what the GPS reports degrees. So the GPS is reporting degrees. So you input those numbers in degrees, and then you have your program recalculate them into radians. Okay, you have it recalculated into radians. And then you do your calculation for distance and heading in the program. So let me just kind of show you what I did here. I can come here now to Google Earth. Now what you want to make sure is you want to make sure that you are in decimal degrees on here. And so let's see, you come down here, and where is that? Tools, you come to options. And then here in options, you want to make sure that you're set on decimal degrees, so your Python program and your Google Earth are working in the same degrees. Okay, so what I can do is I can come here and I can I can come here and I can put this little mark. What did I do? I went up and I got this little pin here, and if I get this, it will tell me the lat, lon, in decimal degrees of this point, okay, and I write that down, and then I move that up here, okay, and then I get these two numbers. I guess you didn't see that, did you? Okay, I move it up here, and I get these two numbers, okay? And then what I can do is I can come back over here and programming those equations. I now have lat 1, ln 1 from that little box, lat 2, ln 2 from that little box. And now I did the calculations that said it was 261 meters and 54 degrees. And so you can even check that, right? We got to make sure that we program the Haversine right before we go in and start trying to put it in our GPS. And now if I get this little ruler tool and I start where I started right here, and I go to where I end, then what does it tell me? It tells me that that is 261 meters and 54 degrees. 261 and 54. 261 and 54. Boom, that's exactly what I calculated. So now what your job now is to come in, here and to use these two equations and to program them up. I think this would be an excellent place to use a function where you could have a function that calculates d, the distance, and you would pass it lat 1, ln 1, lat 2, ln 2 in decimal degrees, and then the function would convert to radians and then calculate first the included angle, and then from that would calculate the distance and then return distance, and then a second function that calculates the heading based on that equation up there. So that is your homework assignment. And then what I want you guys to do then is I want you to go in and then I want you to make a little video in whatever 2 points that you have, just like I did on Google Earth. Show me coordinate 1, show me coordinate 2, and then show me the calculation from your program of what the distance and heading is, and then check it on Google Earth and show me that that works, because we've got to make sure this equation works. We got to make sure this equation works before we jump in and start trying to put it in the GPS. Now, like I say, what you could imagine is I could press the button at location 1, I could press the button again at location 2, and then it could tell me the distance between those two locations, and it could tell me the heading that is between the first point and the second point. So there's a lot of useful things that we can do as we move forward if we can get this Haversine programmed in here well. And so we're going to take a lesson where we just try to get the equations programmed in. Okay, I hope you all are having as much fun taking this class as I am having making it. It's at this point that I always give you guys a great big shout out who are standing with me on Patreon. The only way that I can continue to provide quality, in-depth content every single week is with the support of my Patreons. Big shout out to you guys. You can also help me by giving me a thumbs up on the video and leaving a comment down below. If you haven't already, subscribe to the channel. When you do, make sure you ring that bell so you'll get notifications when future lessons drop. And most importantly, share the video with other people, because the world needs more people working like an engineer and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.